We've determined that in the general multidimensional case of solving the Wiener-Hopf equation using gradient descent, that we can model the convergence behavior to the correct solution as the behavior of the sum of multiple modes. Each mode is a function of one of the eigenvalues of the autocorrelation matrix, and our choice of mu affects how each mode is going to behave. And of course, we get a steady decrease, providing we've chosen a mu that converges, as a function of raising that to a power of 2 to the I. Well, let's use this now to come up with a best choice for mu. We will do this by plotting our absolute value of 1 minus mu lambda k as a function of our choice of mu, and we notice a pattern that emerges. Namely, we get a bunch of what look like v's here. And so what we see, of course, is when mu is equal to 0, all of the terms for every k, 1 minus mu lambda k, are going to be 1. Well, that's not going to converge. So as we increase mu, then since our lambdas are all positive, that's going to decrease the value of 1 minus mu lambda k. When we reach this point, right here, we're going to have 1 over lambda max. That's telling us that the first mode, I guess, converges rather quickly. However, at that time, the slowest mode, the one associated with lambda min, is going to be converging rather slowly, as noted right up here. We would like all of these values to be as low as possible. Well, we could choose, let's take 1 over lambda min, but in this example, at that point, lambda max, the mode associated with lambda max, won't converge at all, because it's back up here in our danger zone, where above this line and inclusive does not converge. So to have the, I guess, the fastest convergence possible for all of the nodes simultaneously, we are going to find the minimum maximum value of 1 minus mu lambda k. And that's going to occur right here. And you'll notice that at this particular point in time, or not point in time, but choice of mu, that we have the intersection of the line for lambda min and the line for lambda max. The other line is in between there someplace, and indeed every other line is going to be in between there. So our fastest overall convergence is determined by lambda min and lambda max. So how do we find out what that point is? Just a little bit of simple algebra. It's necessarily going to be on the downward slope of the lambda min line and the upward slope of the lambda max line. So we'll have negative 1 minus mu lambda max is equal to positive 1 minus mu lambda min. We can now solve for mu over lambda max plus lambda min is equal to positive 2. So for fastest convergence, we have mu is equal to 2 over lambda max plus lambda min.